All right, we're going to look at probability part 2, so really just a continuation of what we were doing before. We're looking at this first exercise. Assume a bag contains 3 blue balls, 2 red balls, and 5 yellow balls. A ball is selected and its color is noted. Then it's replaced back in the bag. A second ball is selected and its color is noted. Find the following probabilities. So we want to know both of them as fractions and decimals. The probability of a red ball and then a yellow one. So a red one, there are 2. So we have 2 out of a total of 3 plus 2 plus 5. That would be a total of 10. And then we have 5 yellow ones. And I automatically put a plus sign, but it's not either or. We want both these events to happen. So we're going to be multiplying that. And that ends up having us get 10 out of 100, which is 1/10, or written as a decimal, 0.1. For the next one, we're going to be looking at the probability of getting yellow and then blue. So yellow, the probability of that happening is 5 out of 10. And getting blue is 3 out of 10. So we're going to have 15 out of 100, which if we reduce by 5, that's 3 out of 20, and then as a decimal, 0.15. Next, we want the probability of blue and red. So blue is going to be the 3 out of 10, and the red is going to be 2 out of 10. So we're going to get 6 out of 100. Which you could reduce that by 2, that'd be 3 out of 20, or as a decimal, 0.06. Now to get blue and blue, probability is going to be 3 out of 10 times 3 out of 10, which will be 9 out of 100, which is 900ths. As a decimal, we have that. I'm asked if these events are independent or dependent. They're totally independent because you put the ball back in, so it doesn't matter what happened with that first one. So we are going to say independent. Because it's the same, the probability of the second draw is the same whether the first event happened or not. That's why we say it's independent. All right, for exercise number 2, we're going to assume the bag contains 3 blue marbles, 2 red balls, and 5 yellow balls. So same situation there, but now it's going to not be replaced back in the bag. All right, so let's see what that means. We have the probability for this first one of red and yellow. So if we think about the red one, there are 2, and so the probability of getting that is going to be 2 out of 10. But next we want to get a yellow one, which is going to be 5, but because we didn't replace the last marble, it's only out of 9 possibilities. So this is going to be 10 out of 90, which is 1/9. As a decimal, that would be 0.111, so we'll say 0.11. All right, next we have the probability of blue and blue. So the probability of a first one being blue is going to be 3 out of the 10. And then the next one, there's only 2 to choose from now, and there are only 9 marbles. So notice that both the numerator and denominator here are reduced by 1 because it was the same color again. So we're going to get 6 out of 90 for that. That could reduce to 1/15, which is approximately 0.07. Not sure where that line came from there. Okay, let's see. For the next one, we're looking at yellow and red. So the probability of yellow was 5 out of 10. And so then getting a red one, again, those are kind of separate. It does depend on each other that we have fewer marbles, but we still have those 2 red ones because we didn't choose one yet. So that's going to be 10 out of 90, which is that same 1/9, which is about 0.1 1. Now if we want to be not blue and not blue, so let's think about if we're not blue, then that would mean we're either red or yellow. So there are 7 ways to be not blue, even though I'm drawing this with blue. Once you choose the not blue one, then there's only going to be 6 that are not blue after that out of 9. So we're going to have 42 out of 90, which reduces to 7/15 as a decimal. That's about 0.47. Now these ones are, when asked to be independent or dependent, these are for sure dependent on each other, because if you know the first, it changes the probability of second, because we had to like reduce the number of marbles. All right, I'm going to switch over here, and what we were actually doing was using conditional probability. So you can see it's similar to what we've done before when we have 2 events happening. So we would normally see the probability of A times the probability of B, but if they are not independent, meaning they are dependent, then we're going to look at this basically condition. We read this as the probability to be given that A happened. So if you know that first event happened, how is that probability to be kind of changing up? So for example 3, we're looking at this table, and it's all about blood types. We have O, A, B, and AB, and it's connected RH factor. So we hear like A positive or B negative. So we're going to consider the figures below, which shows the distribution of these groups for Americans. We're going to choose one American at random, and we want to find the probability of the following. So we're looking at the probability of O negative. So if I look at the O column, the negative for that is 6%. So we're just going to have 6%. Okay, it would be the probability of a random American having that blood type. All right. So for the next part, we're looking at, really, it's a conditional probability that they have O blood given that they're RH positive. I'm going to go back to that definition really quick, and I want to rewrite this one other way. And so if I go here, what we could do, if we had the probability of A and B equal to probability of A times the probability of B given A, we can actually get that alone by dividing by the probability of A. And so what that means is the probability of B given A can be written as the probability of A and B over the probability of A. And that's really the situation that we have here. And so the probability that they have O blood and they're RH positive, if I can go back here, it's going to be this 37%. So we have 37, but that's not out of the, we're really not talking about out of 100 anymore, because we are given that they're RH positive. We're really just focused on the total going on here. So if I add the 37, 34, 10, and 4 together, that's really only 85% of the population. But if that's given to us, that's what we're going to be looking at. We're going to take that 37 out of the 85, which dividing that gets us about 0.435. So notice that this is really like 43.5%. It's an increase from the 37 because we have a smaller group that we're looking at. We're not looking at the whole, that 100%. For the next one, we want the probability that they are A positive or AB negative. So the probability that they're A positive, let's see if I can erase, doesn't like erasing some of this. Oh well, let's see. A positive is going to be this 34%, and AB negative would be the 1%. And so we don't have a conditional probability here, so we're going to be at 35%. For the last one, it says RH negative, but again, we're given that that person has B blood. So we're going to look at the B blood. So B blood is right here, and that's actually 12% of this population. So the probability that they're negative, knowing they're that little population, is going to be that 2. So we're going to have 2 out of that 12, which is 1/6, and as a decimal will be about 0.17. So we can say it's about 17%. So again, knowing that they have B blood, there's a 17% probability that it would be negative. All right. I stuck in a picture, there's a picture of a deck of cards here, just in case that's not familiar to you. It has all of them, and I know we've done a few problems already kind of talking about it, but you can see that there are 4 suits here, and that's the shape that's on the card. And so the top one is our, oopsie, not clubs. The top one we call clubs. Okay, so that shape looks like a little clover leaf is clubs. The spade, like a shovel looking thing, that's what I can think of. And then we have the heart, and we have the diamond. So there's 4 different ones of these. These are called suits. And within each suit, the cards kind of count up from 1 all the way to 10. And then we go Jack, Queen, King. That's how they kind of increase. Some people think about Jack as like 11, Queen is 12, and King as 13 if you wanted to assign a number value to them. And that number value is, we call that the rank. So when we go over to our next page here, we're looking at just some simple probabilities, looking at a deck of cards, and we're going to be drawing just a single card. So the probability of getting a king, well, remember that there were 4 different suits, so there's 4 different kings, and there are, a standard deck has 52 cards, so we're talking about 4 out of 52. Which we could reduce to 1/13. Which again makes sense because out of 13 cards, which is one of the suits, there's only one that is a king. The probability that your heart, well, there's 13 total ranks, so we're going to have 13 out of those 52 cards that will be hearts. We could reduce that to 1/4, and again, that's because there are 4 suits, so a quarter of them, 1/4 of them are that suit. A face card, there was again Jack, Queen, King of each suit. So there are 4 suits and 3 cards. And that's going to be 12 different options. And again, you can go back if you want to and look at, this is our entire sample space. And so you can count and see how, I said there's 3 of them, but there's times 4 suits. I mean, not suits, face cards. So that's 12 out of 52, which is reducing to 3/13. Black cards, that's half the deck. That's 26 out of 52, or you could just say that that is 1/2. Now imagine that you have a card is drawn, then replaced, and then a second card is drawn. We are replacing this time, so they are going to be independent events. So the probability of getting a king, remember there are 4 kings to choose from, and getting a 5 also, there's 4 to choose from. Again, it was replaced, so we'll still have out of 52. This reduces to 1 out of 169, which is about 0.06. Next, we have the probability of getting a 10 of hearts. That is one particular card out of the 52, so it's 1 out of 52 is the probability of that. Getting a club, there's 13 of that particular suit out of 52. So we're going to reduce that. That's going to be 1 out of 208 and multiply that on a calculator, which will get you about 0.005 is our probability. Now getting a diamond, again, there's 13 diamonds in our deck. We take that card out, or the probability of getting that card is 13 out of 52. Put it back in, get another one, same probability. So we multiply those, it will become 1/16, which is about 0.0625. Now to get aces, an ace, there is only 4 aces out of the 52 cards. So we're going to have 4 out of 52 times 4 out of 52, which becomes 1 over 169 again, which is about 0.006. Now exercise 6 just changes it up a little bit because it says that we are not replacing. So if we're not replacing, this is going to be, these are going to be not independent. They're going to be dependent. So the probability of getting a king is 4 out of 52. Now getting a 5, there's still 4 5s to choose from, but the deck is 1 less, so it's out of 51. So we'll get 4 out of 663. You can change it to a decimal too if you want to. I just left that as a fraction. Now a 10 of hearts, there's 1 of those out of 52. To get a club, there's 13 of that suit, but again, out of 51. So those are not independent, so it's changing it up a little bit. So we get 1 out of 204. So again, notice that these are the same exact questions that we had before, but it really matters if you say that they're replaced or not replaced. They're not replaced, we have that dependence. So getting a diamond, there are 13 out of 52. And the next one being a diamond also, there's only 12 out of 51. And multiplying that and reducing, we get 1/17. For aces, there are 4 out of 52. Again, once you choose that, there's only 3 left out of 51. Multiplying and then reducing, that's 1 out of 221. All right, and for our last page, we're gonna up it. So first we're just selecting 1 card at a time. Then we're gonna select 2 cards, 1 at a time. And then we're gonna do one where we replace it and not replace it. Now we're gonna look at 5-card poker. So that means we're gonna select 5 cards from a deck of 52. So the sample space is all the 5-card hands. And so we want to think about all the different combinations that you could get with 5 cards. And to actually count that, we're going to use our combinatorics. And I'm going to write it, that fancy notation, 52C5. You can enter that on your calculator. Remember, it might look like NCR, and then you write 52,5. Those are all the same. If you plug into the formula, my favorite is with permutations because it's really thinking about it in terms of permutations. But then you're going to divide out all the ones that are the same. And so we divide by that 5. When you do that, we should get 2,598,960. So there are a lot of 5-card options. So when we go to look at getting a hand that has 4 kings in it, we want to take those 4 kings and see how many ways we can arrange them. It's kind of boring. I could write it with combinations, but really like 4C4. There's 4 kings. We're going to choose 4. That can really only happen one way. You could punch that into your calculator. But we have 5-card hands, so we still have a 5th card we need, and that's not a king. So 48 cards are not kings. And we're going to choose only one of them. And so those are the different ways that we can get the hand with 4 kings. So if we want to calculate the probability of that, it's going to be out of all the possible 5-card hands. So out of 52C5. So when we calculate this, we're going to get 1 times 48 over the 2598960, which reduces to really 1 out of 54145. Or about 0.00001,847. And if you want to turn it into a percent, it's 0.00, about 2%. Very unlikely. And what I wanted to show you in the calculator really quick, you could enter that entire thing into the calculator. So I start by clicking on the fraction, and I'm going to type in there the combination 4C4, so 4,4. Close that up. And then I'm going to say times the combination. Go to function, NCR, go back to main. It will be 48,1. And then I'm going to put on the bottom there the 52. So combination again, function, NCR, 52,5. And so it gave me this thing, which is in scientific notation. So that -5 really means to divide by 10 5 times, which moves our decimal point over 5 times. And so that's where my decimal came from. It put 4 zeros in the front of the number 1847. And then you can see that I just changed it to a percent by kind of moving it back 2 spaces. So then looking at the next one, the probability hand with all spades. So we know that the spades are what we're looking at. There's 13 of those, and we're going to choose 5, and that's all 5 of my cards. So we're going to take that divided by the possible 5 card hands. And again, if I bring my calculator out, let's kind of scoot this in. We'll go to that next one. And so I'm going to enter in those combinations. So I go to function, NCR, and I'm going to enter 13, 5. That's my numerator. So I'm going to put divide symbol, and that makes that fraction bar, or I could have written the fraction at the very beginning. I could have clicked on that. So when I'm inside, let's see, in the denominator, I'm going to write function NCR. Oops, didn't click on the bottom. There we go. NCR, go back to the main, and we're going to say 52, 5. Again, it's giving it to us in that scientific notation. So that -4 again, that 10 says divide by 10 4 times. That moves us over 1, 2, 3, 4 spots, which puts 3 zeros in the front. So this is going to be 0.123495, which as a percent, if I just move the decimal 2 places back, it's going to be 0.05%, about. All right, and the last one here, the probability of any 4 of a kind. So the first thing that we're going to do when we think about all the different ways is choose what 4 of a kind. So there's 13 ranks to choose from. We're going to choose one of them. Once we know what rank is, there's going to be 4 of those to choose from. So this is find the rank. And then this is we have the rank. And then we're going to choose 40, so 4 of those cards. So we still need one more. So there's 48 that are not that rank, and we're going to choose 1, all out of 52C5. So then with our calculator, it ends up that 13C1 is just 13, 4C4 is just 1, 48C1 is going to be equal to 48. Over the 2598960. This is going to be 624. Again, you can enter it into your calculator. It's kind of nice to do these like kind of small side steps. And so we end up the 1 over 4165, which when you punch that into your calculator ends up being 0.00024. Again, if I want to write it as a decimal or as a percent, I'll move that back twice, so 0.24%. So you can see these percents are quite small, which means these are poker hands that are highly unlikely, and that's when you win. You get the person who gets the hand with the lowest probability. So hope that made sense.